Okay, so today we're going to finish up on graphs. I know that it seems like we should be spending a lot more time on this. The thing about graphs is it's a very deep subject, and hopefully you will spend more time about it in algorithms, because that's where most of graph study or study of graphs is inside of algorithms. Because when it comes down to it, there's mainly two ways people represent a graph: adjacency matrix and adjacency list. Those are the data structures. So that's why we're just covering those two. But keep in mind that graphs are actually a huge research section in computer science, and is way more than what I can teach you just now. I mean, you could do full courses on just graphs and still not cover everything. All right, real quick, what did we talk about last time? We talked about graphs. We got some of the terminology down. Let's see if we remember that. What does it mean if, well, actually, what does a graph contain? There we go.
Numbers. Data not what connects to what.
What connects to what? All right. What are the two? A graph is a set of two things.
Points and lines.
Vertices, edges.
Yeah, vertices and edges. You're using points and probably movement. Vertices and edges. Now, vertex and node are interchangeable. I'm going to use them interchangeably, mainly because I think node is going to make more sense since that's what we've been using so long. But keep in mind that if someone says vertex, that's a node, and then the edges is what connects them. All right. And then, so if something's adjacent, what does that mean?
Besides, they're connected.
They're connected. All right. A little more, I think you're on the right track. A little more precise.
There's an edge going in that, what's called direction?
Right. Okay. So two nodes are adjacent if there is an edge between them. All right. Oh, now what is a path?
It's the way you follow the edges.
We gotta think more about. Have any of y'all taken discrete yet? Nope. Curses. Yeah, this is where it gets a little tricky. So it's the set of edges from one node to another, or a set. Can there be multiple paths? Yes, of course. Could there be no paths?
Yes.
Right. All right. What does it mean if a graph has a cycle or a loop? Yeah, so there's a path that basically starts at one point and then comes back to itself. I'm sorry?
How can there be no path?
Oh, well, that's easy.
You don't go from one path to
So node 0, node 1. Is there a path between 0 and 1? No.
Okay. I wasn't here last time, so.
Yeah, I understand.
Catch up.
All right, represents graphs, computer memory, blah, blah, blah. We talked about shortest path algorithm, which actually computed the shortest path from one node to any other node. Talked about a bridge problem. All right, let's go look at some more pictures of graphs. Here we go. That's good. This was a good review. Can anyone tell me a cycle in here?
Oh, the left or right?
0, 3, 6, back to 0. Yep, that's one cycle. Are there any others?
0, 1, 2, back to 3.
Yep, 0, 1, 2, back to 0. Let me see if there's any other.
4,
Yeah.
8, 5.
Say again?
4, 8, 5.
Yeah, 4, 8, 5. 4, 8, 5. Oh, there's another one.
0, 3, 4, 8, 6.
Yeah. Boom, 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 boom. Okay. I just realized you got 0, 1, 5, 8, 6, 0.
But there's an arrow from 8 to 5. Does that not matter?
Oh, I'm sorry. Yeah, you're correct. So you can't go from here. You'd have to go from 0, 1, 5, 4, 8, 6, back to 0. There's another cycle. Yes, the arrow is very important. It's easy to, if you have arrows like this, what type of graph is it?
Directed.
Directed, right. If you don't have an arrow, that means it's undirected. So just assume, the easiest way to think about this is always assume all graphs are directed. If they don't have arrows, that means they have an edge going both ways. That's just, if you keep it that way, you're going to be a lot happier, trust me. All right, blah, blah, blah. We went through a lot of different representation. Oh, I just erased it from the board. But what was the point of the adjacency matrix? What was it storing? Actually, let's go and do a quick review on the board. Yes. 2, 3, and 4. All right, give me some numbers. Positive
7,
numbers. 7,
3, 14,
8,
11.
350.
Wow, it's really expensive to go from 4 to 0.
6, 33.
All right. Morning. So if we're going to do the matrix, so how many elements, how many rows, and how many columns are going to be in the matrix representation of this? 5 by 5. Why are there 5 by 5? Because that's how many nodes we have. So 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. All right. So what's going to be inside of each of these cells? The weight of, right, -1 or the weight of, right. So what's the weight from 0 to 0? Right, because if you're already there, it doesn't cost anything to do it. How about from 0 to 1? 7. It's right there. 0 to 2. -1, it doesn't exist. Notice that a path may exist, but there's no direct edge between 0 and 2. How about 0 to 3? 1, 0 to 4? All right. How about from 1 to 0? 8, yes. There are edges going both ways, but this one costs more. How about from 1 to 1?
0.
1 to 2? 1, 2, 3? 3. And then we got 1 to 4? Wow. 1 is the place to be. How about 2? 2 to 0? Yeah, there's no edge from 2 to 0. 2 to 1? Yeah, there's no edge from 2 to 1. 2 to 2? Yep, we're doing great. 2 to 3? 2 to 4? All right, we're doing great. 3 to 0. 3 to 1. 3 to 2. 3 to 3?
0.
And 3 to 4? Yep. 4 to 0. 250. 4 to 1? Yeah, then you got a big 0. All right, great. Okay, so what's a... All right, so this is the adjacency matrix, which is a way to represent a graph. You just need to store this in memory, and that's your graph representation. Right now, let me make sure this is clear. One of the biggest advantages of the adjacency matrix is what is the big O of finding the weight between two edges? O of 1. Right, because you just jump to the memory location, you're done. That's the big advantage here. Can anyone see what's a disadvantage? Y'all said a bunch of things. I didn't hear you. Yeah, sure.
Lots of wasted space.
Lots of wasted
Since
space.
If you don't have edges, it will make lots of -1s get placed, and you're not using that information there.
Right. So there's a lot. To make this even bigger, what if it's a million? You got a million nodes, and but you only have maybe 2 million edges. How much memory would be required if you have a million nodes to use an adjacency matrix?
Oh, geez. A million.
Times a million, right? Which is 10 to the 12th. What's that, trillion? Trillion. So, yeah, times 4. If we're saying they each take 4 bytes, so that'd be 4 terabytes of memory. All right, who's got it? No one? Okay. All right. But you're really only storing the edges, which means you're only storing 2 million edges. 2 million times 4 is 8. You're really only storing 8 megabytes of information, but you're consuming 4 terabytes of information. many orders of magnitude difference. So that's the problem with the adjacency matrix, and is why in general an adjacency list is used instead, because of the memory problem. I started with the matrix because I think it's a lot easier to understand, but the list is in general how people are going to implement it. Oh, that's my favorite program.
Why?
Yes? Why is yes my favorite program? You know how you sometimes have, thank you. You have programs that ask, are you sure you want to do this? And you hit yes. Are you sure you want to do this? You hit yes. What yes does is it automatically says yes to everything.
Really?
Yes. So you take yes, pipe it to what your program is, yes, 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 yes. One of my favorite ones. You can also configure it to say no, but that's not its default. Okay, where are we? So that was the matrix. The list. So the list is going to act a little differently. You have, well, it's going to be essentially an array of linked list. Hey, where's that? Have you heard that before?
Yeah.
Oh, where was that? Hash tables, right. But the idea is the number you're going to have, n nodes of linked lists. In other words, there's going to be a linked list associated with every node. So if you have 5 nodes, how many linked lists you have? 5. Okay, great. You have 1,000,000 nodes, you have how many linked lists? 1,000,000. Okay, great. But a linked list can start off as empty, so you don't have to store everything initially. Okay, that's yeah, we'll leave that on the board, but let's go do the adjacency list version of this. I'm going to have to erase this for space. So the adjacency list, you're going to have first off your array of linked list. So 0, 1, 2, 3, 4. So this is your array. And I'm having the arrow point over. Why do I have these arrows? Because they're pointing, yeah, they're pointing to a linked list. So initially these are all empty. That's how they start. But we want to represent this over here. So let me make sure I stick with the slides presentation. Oh, they don't hold the weight. Well, that's not nice.
Wait, what happened?
They didn't hold the weight,
What did?
the slides. So I'm going to create a struct, and it's going to contain int mdest for the destination, and we'll just say wm weight. And it's a linked list of these structs. So I'm just going to call it a pair for now. It's really just a pair. And we'll have the first one be the destination and the second one be the weight. Okay? All right. So if we're going to do that for 0, where can you go from 0? 1. And what's the weight?
7.
So you'd have 1, 7, and that's it. So it's a linked list of pairs, and right now it only has 1, 7. Okay.
Wow, that's a lot easier.
Maybe. This is harder to code up, but it's way more memory efficient. All right, so how about 1? Where can we go from 1? Can we go to 0? 0, how much does it cost? 8. Can we go anywhere else? Can we go to 2? That costs 3. And we can go to 3, and that costs 33. Can we go to 4? Yeah, we can go to 4, and that costs 6. Yeah. All right. How about for 2?
You can only go to 3.
You can only go to 3, so we're just going to store that. 14. Okay. How about 3? You can only go to 4. Oops. I just realized I'm doing this for you. How about 4? So what do I write?
4.
So you're at 4. You can go to 0, and the weight is 250. Okay,
Lot more space.
here's less space. If you want to find the weight between two edges, what's the big O now? Worst case O of N, yep. Because now it depends on the size of the linked list.
Best case always.
Oh, yeah, best case O of 1.
But that's almost like
What would be the average?
average mode.
Oh, what? Well, that's okay. So let's see if I can ask this question correctly.
Technically always.
All right, so which data structure is better?
It depends.
Oh, there we go. Well, that was good. What does it depend on?
Well, it depends on lots of factors, sizes, how fast.
We're going to have to do a research paper about how we can gauge the efficiency of all algorithms based on their based on integrating bubble sort into the algorithm somehow. So we're gonna,
That sounds great.
Just have a good project comes up whole.
We need to implement a data structure called bubble sort.
Bubble-
Be the best data structure.
but it's an algorithm. All right, so it depends. What does it depend on?
Your applications.
Performance,
Yeah, your
scenario,
application.
implementation.
Okay, yes, good high level answer. How about specifically? Good high level answer, good high level, but more specifically.
For this, exactly.
What,
The size of your,
I mean, yeah, it depends. What is it going to depend on?
the size of.
The graph.
Yeah.
What about the graph does it depend on?
How many edges there are.
Right, so how many edges? So if the graph is fully connected, which is better? The matrix, right, because you're just going to fill it all out and you can just look it all up. If it's sparse,
Oh,
the list is better because you have few, you may have a million nodes, and on average, each node is going to have 2 edges. Obviously, the list is going to be better here.
If it was like a graph where it can only have one output per input, then you could just use that.
Well, yeah. Right. But that would also just be a linked list. So, doesn't help too much. We would be able to add and remove edges on the fly, as well as adding nodes. Yep. Okay. Great. Let's see. I think we covered that fairly well. Let's see what else the slides say. So this is their representation. Notice that they did not put in the weights, which is terrible, but oh well.
Bad slides.
Bad slides. All right, so we want to be able to create the graph, clear the graph, make the graph empty, determine whether the graph is empty, traverse the graph, which we talked about last time, and print the graph. Okay, great. Blah, 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 blah. I don't even know if these slides are meaningful. Didn't we already do these two? Depth first and breadth first? Yeah. Okay. Well, we coded one of them. You understand them. Okay. All right, so real quick, let's see if we can go over here. If we were going to do a depth first traversal, what would be the order? I wonder if they'll be different. So you start at 0, and you visit 0. So we're at 0. Then where do we go? To 1, right, because that's the next lowest one. 1. We're at 1. What happens next? We go to 2. We're at 2. Where do we go next? 3. I think they're all going to be the same because of how this works out. So I'm going to remove this edge. If I remove that edge, by the way, what do I have to edit over here?
Do one.
Right here. Yep, there we go. All right, we go 0, 1, 2, 3, and then 4. Okay? Everyone see that? You're going depth because you're starting and you're trying to go as far as you can first. So let's go breadth first. Remember, you're going out. You're doing your breadth first, I'm going to go ahead and write the Q down here because that's what you use when you implement it. When you start, you add the first node, which is 0. Great. So what happens? You pop the front of the Q and you go visit it. We pop it, we visit 0, and then we add all the elements we can visit from 0. What are those? 1. All right, so we add that to the Q. All right, those have all been added. We go back to the Q. We pop the first one, which is a 1. We put it up here. We add all the elements 1 can visit. What are those? And that we haven't visited before. Sorry. 2 and 4. We don't add 0 because we already visited 0. All right, so we're done there. Now we're going to pop the front, which is a 2. We're going to visit the 2, and then we're going to add all the elements of 2 that we can visit that we haven't visited before, and that is, notice the 3 goes after the 4 because it was put on afterwards. So now we're going to go and visit the next element of the Q, which is a 4. Am I still on the screen? Yes. Add all the elements we can go to 4 that we haven't visited before, and that is nothing. We've already visited 0. So we pop the next element, which is the 3, visit it. We look at all the elements of 3 that we can visit that we haven't visited before. That's nothing. The Q is empty. We're done. Do y'all see how that was different? Do you need maybe a clearer example of the difference here? I'll have to erase all this, but I can give you a clearer example. This is confusing because I'm getting the twitch look.
Yes, please.
Okay. Well, I have to erase this board, unfortunately. Oh no! I'm going to write 0 to 1. It makes a lot more sense if we first think of it as a binary tree.
Okay.
Okay. What is the depth first traversal of this? 0. We go visit the left, come back up, visit the 4, come back up, 2, then 5, back up to 2 to 6. So it goes 0, 1, 3, 4, 2, 5, 6. You see how that happened? 0, 1, 3, 4, 2, 5, 6.
And it always favors the left first.
It always goes down the left first, or it goes down the lowest element first. All right, breath. Visit 0.
Okay.
Find all the elements that 0 can visit, which are 1 and 2. We're going to visit those next. We visit 1 and 2 next. Now we visit all the elements those can visit.
It does it. It's like it does it in levels.
Yes.
Oh.
And then if there's anything under here, it would then visit that afterwards. So remember, depth is going all the way down. It's going to the depth, while breadth is expanding out, trying to visit everything at once.
Huh.
Hence the term depth and breadth. All right. Okay. Now let's see what we got. I think we're actually almost done. Did shortest path, that's great. And then next will come prims, minimum spanning tree. Oh, fun. Okay, we will talk about minimum spanning tree after we do a little work on the lab.